Okay, let me start with discussing about the intended learning outcomes and topics for this morning and for this week. So at the end of this module, the students should be able to discuss linear and nonlinear applications of operational amplifiers, and then analyze operational amplifiers with negative feedback. Explain a current to voltage converter and voltage to current converter, and discuss the operation of a zero level detector and non-zero level detector. So the following will be our topics. So we'll discuss about linear and nonlinear operational amplifiers, and then operational amplifiers with negative feedback, inverting operational amplifiers, and then voltage follower, non-inverting operational amplifiers, zero level detector and non-zero level detector. We'll also discuss about Schmitt trigger. Okay, so those are the following topics that we'll cover. So this module 2 will also be included in your preliminary exams. So your preliminary exam, I will announce it later. Okay, so let's proceed with the PowerPoint presentation. So you can find your PowerPoint presentation here in the instructional materials. Let me just open it so that we can start with the operational amplifiers. Okay, let me just enter the full screen. I hope that the screen is clear. Okay, so I think we can begin now. So the title of our topic is about linear and nonlinear applications of operational amplifiers, and the objective of this topic is already discussed. I have already discussed the objectives of the module a while ago, so I will not include it here. So let's start. So in case that you have some questions, just you can use the microphone, because I am now in the full screen mode and I can see your messages. So from time to time I would like to check on the messages, but I cannot check it all the time. Okay, so you can just use the microphone if you want to ask some questions. Okay, let's discuss this. So the first thing that I would like to discuss is about linear and nonlinear circuit. Okay, so a circuit is said to be linear if there exists a linear relationship between its input and the output. Similarly, a circuit is said to be nonlinear if there exists a nonlinear relationship between its input and the output. Simply, we can say that the linear circuit is an electric circuit, and the parameters of this circuit are, for example, resistance, capacitance, inductance, and etc. And they are constant. However, the nonlinear circuit is also an electric circuit, and the parameters of this circuit differ with respect to the current and the voltage. So that's the definition of the linear and nonlinear circuits. Now, in terms of classification of operational amplifiers, especially its operations, there are two classifications. So we have the linear applications and the nonlinear applications. So basically, in linear operational circuits, the output voltage or current is directly proportional to either input voltage or current. And this type of linear application is acting as an amplifier. On the other hand, the nonlinear application is acting as a switching or as a switch. Okay, so this is in the amplifier mode, while the other one is in the switching mode. In nonlinear operational amplifier circuits, the output signal is not directly proportional. So you can see the opposite definition of the two. The linear application is directly proportional, okay, to the input signal of the voltage or the current, while on the other hand, the linear operational amplifier is not, the output signal is not directly proportional to the input signal. Okay, so those are the difference between the classification of the two linear applications, and then we are going to discuss some examples of the linear applications and the non-linear applications of the operational amplifiers. Okay, let's proceed. So these are some of the examples of for linear applications of operational amplifiers. So we have the inverting amplifiers and as well as the non-inverting amplifiers. We also have voltage followers, and then we have the integrator amplifiers and differentiator amplifiers, and then we have the current to voltage converter and the voltage to current converter. So these are some of the examples that we're going to discuss today. Then we also have some of the examples of for nonlinear applications of operational amplifiers. Okay, and in here we have zero crossing detectors, and then we have non-zero crossing detectors. We also have voltage comparators and the Schmitt triggers, right? So let's begin to discuss the examples of the linear applications of the operational amplifiers. So we have the non-inverting amplifiers here. So a non-inverting amplifier, this is a type of operational amplifier, a class of a op-amp, and it is an op-amp circuit configuration that produces an amplified output signal. So basically it's acting as an amplifier. Okay, and this output signal of the non-inverting operational amplifier is in phase. So we have in phase with the input signal applied. So whatever is the input signal applied, the signal of that is along with the phase of the output. So in other words, a non-inverting amplifier behaves like a voltage follower circuit. Okay, we will discuss about voltage follower circuit later. So in this particular illustration that you can see from here, we have a input voltage here. We have that load, and it's connected to the inverting signal of the amplifier, and then we have the non-inverting signal. Okay, and you can see from here the non-inverting signal is connected to the output of the amplifier. Okay, and that circuit is what we call the feedback circuit. So if you want to compute for the value of that voltage follower circuit, okay, so that will be computed as the values of the output voltage multiplied by the resistor here, which is Ri, this one, divided by the sum of the resistors Ri and the Rf resistor, which are all considered to be the feedback circuit. Okay? Now, from this equation and from this particular non-inverting amplifier, we can also derive the formula for our output voltage. And the formula for getting the output voltage will be equivalent to the open loop gain multiplied by the input minus the voltage follower. Okay? So we can also derive the formula for the B, no, which is the attenuation. So B here is what we call the attenuation. It's computed as the Ri over Ri plus Rf multiplied by the B. Okay, so therefore the general formula for the output voltage will be the following. So the open loop gain is multiplied by the difference of the product of the output voltage multiplied by the attenuation, subtracted it from the input voltage. Now, if you want to compute for the closed loop gain of the non-inverting amplifier such as this circuit, the non-inverting formula for the closed loop gain will be equal to the sum of 1 plus Rf over Ri. So basically ito yung gagamitin natin formula for that. Okay? So that's the formulas that we can derive from this circuit. Okay? So as an example, so we have here a non-inverting amplifier. So we are asked to determine the closed loop voltage gain of this particular amplifier. So we have the as you can see, the non-inverting amplifier here is connected to the output voltage. So we have the feedback circuit here. The RF is equivalent to 100 kilo ohms and the RI is equivalent to 4.7 kilo ohms. So our solution would be to use the and we are asked to determine the closed loop voltage, no? So the closed loop voltage gain is this one. Okay, this is the closed loop voltage. So if we want to compute for that, we just substitute the values of the 1 plus Rf over Ri. So that will be equal to 1 plus 100 kilo ohms divided by 4.7 kilo ohms, and that will be around 22.3. So this is unitless because we are computing for the closed loop gain of this non-inverting amplifier. Okay, so finally we have the answer 22.3. So I noticed in your assignment, no, that you have submitted, some of you have used the siguro ang preferred ko na lang na method of submission of the assignment is kasi iba-iba yung ano nyo, yung mga submissions nyo. Some made it in a scratch paper, and then when they computed their solutions, they just took a picture of their computations and then submit it or pasted it in their Microsoft Word document and submit the assignment. However, some of you did it in a computerized manner. So siguro mas maganda tingnan yung Microsoft Word document na lang, no? So for example, you can just make the solution similar as this one, no? So your final answer should be highlighted, okay? Because in some cases, I cannot find the answer, okay? And there are some boxes that were drawn, but that box is for the formula. So paano ba tayo talaga dapat gumawa ng well-presented report? When we present a report, it's typically like you are given the problem such as this, and then a circuit is drawn. So maybe you can also draw the circuit if there is a circuit. Okay, you can just copy the circuit from the problem if there is, but if there is no circuit, then you have to include the problem. Okay, and then of course the solution. So for the solution, you can write the formula, and then you can just substitute the values of the parameters in the formula, and then compute. Okay, and then you can just highlight the final answer, such as this example. So I want to see a well-prepared report, no? So maybe I don't want to see your handwriting na lang, no? Because some of the handwriting is not that good. However, there are some no? So there are some students who wrote amazingly. Okay? All right, so next time I want to see some well-prepared report from you. Okay? So let me just see it next time in your next assignment. Okay? So this is the solution for this particular example. So as I have mentioned a while ago, the nonlinear circuit, or sorry, the non-inverting amplifier, no, such as this one, is behaving like a voltage follower circuit. So in a voltage follower circuit, you can see from here, the voltage follower is typically the same as the circuit of the non-inverting amplifier. However, in this particular illustration, you will see that the circuit, the inverting voltage is connected to the output. In the non-inverting amplifier, the one that is connected to the output is the non-inverting voltage. Okay? However, in this case, the voltage follower, the load is connected to the non-inverting part or input of the amplifier, and the inverting input of the amplifier is connected to its output. So therefore, the definition states that the voltage follower is a special case of the non-inverting amplifier where all the output voltage is fed back, okay, to the inverting input. So you can see here the output voltage is fed back to the inverting input by a straight connection. Some of the important features are its very high input impedance and its very low output impedance. So basically, this operational amplifier circuit, whose output voltage straight away follows the input voltage, that is output voltage is equivalent to the input voltage. Okay, so whatever it is, the input voltage will be the output voltage, and this circuit does not provide any amplification actually. So definitely the voltage gain, as you can see from the example here, we have a voltage gain of a closed loop voltage follower that will be equal to 1, meaning they are similar to a discrete emitter follower, this particular circuit. So when you see a voltage follower, the voltage gain of that is equivalent to 1, okay, because the ratio of the of this particular circuit will be equal to the ratio of the output voltage and the input voltage. But if they are the same, then if we divide the output voltage from the input voltage, that will be equivalent to 1. Okay, so that will be the case. Okay, any questions so far? So you can see also from here that this means that if the input pulse is positive, okay, then the output pulse will be also positive. Okay, so let's proceed with the next example. So this one is the inverting amplifier. Okay, so this is the this amplifier circuit, which is inverting, is connected with feedback to produce a closed loop operation. So this is different from the non-inverting amplifier. So you can see here the inverting input, okay, which is V2 from this illustration. The inverting input is connected to the output voltage. Okay, so here you can see a virtual earth summing point. What is this virtual earth summing point? So we'll discuss that a little later. Okay, what is this point? But you can see this point is connected to the inverting input. Okay, now when dealing with operational amplifiers, there are two very important rules to remember about inverting amplifiers, and they are the following. Number one, no current flows into the input terminal. So whatever it is, okay, in the input terminal, you can see there is no current that is flowing here. Okay, and that V1, this V1 will always be equal to V2. So whatever it is, the input here in the inverting amplifier will also be the input to the non-inverting input of this amplifier. All right, so this inverting amplifier is also known as inverting operational amplifier or an inverting op-amp. Okay, and it's a type of op-amp circuit which produces an output, okay, which is out of phase with respect to its input by 180 degrees. So definitely that definition will mean that if the input pulse is positive, for example, then the output pulse will be negative. But if the input pulse is negative, the output pulse will be positive. So that will be the case because of the definition that the phase, this circuit produces an output which is out of phase with respect to its input by 180 degrees. So it's a complete opposite, So definitely that's the concept of inverting amplifier. It inverts the pulse of the input, so definitely the output will be 180 degrees reverse of that input. Okay, so what is this virtual earth summing point? In electronics, this virtual earth summing point is also called a virtual ground, okay, or virtual earth. And this is a node of a circuit that is maintained at a steady reference potential, so without being connected directly to the reference potential. And in some cases, the reference potential is considered to be of the surface of the earth, okay, and the reference node is called ground or earth as a consequence. And this virtual ground concept aids the circuit analysis in operational amplifier and other circuits, and provides useful practical circuit effects that would be difficult to achieve in other ways. Okay, so that's the explanation of this. So we have here some formulas. So if we want to compute for the closed loop gain of the inverting amplifier, the formula will be to compute for the value of the resistor follower here, which is this one, okay, over here, and then we have to divide it by the input resistor. Okay, so that will be the computation of the inverting amplifier's closed loop gain. Okay, so we can also compute for the impedances of the non-inverting amplifier, and the impedance can be computed as Ri. Actually, we need to compute first for the attenuation. The attenuation will be computed as Ri. Okay, actually this should be Ri divided by Ri plus Rf. Okay, so this one, these two resistors here, so we will compute for the Ri divided by Ri plus Rf. So that will be the attenuation. And then similar to the formula that we have in the inverting amplifier, but this time we're going to compute for the impedance of the of this amplifier, for this non-inverting amplifier. Okay, so we can compute it as the impedance will be equal to the 1 plus the open loop gain multiplied by the attenuation, okay, multiplied by the input impedance. Okay, so the input impedance is not the same as this. Okay, so we will we'll have to compute for the input impedance first. So usually this one is given in some problems, and then what are we supposed to look for is for the input impedance for the non-inverting amplifier. Okay, for the inverting amplifier there is also a formula for that. However, in this case we're looking for the input impedance of the non-inverting amplifier, and this is the formula for that. Okay, so remember also the circuit for the non-inverting amplifier. Okay, now this is an example of the non-inverting amplifier. We are asked to determine the input and the output impedances of the amplifier, this one. Okay, so we have an RF of 220 kilo ohms, and then we have an Ri of 10 kilo ohms. Okay, so the operational amplifier's datasheet gives an input impedance. So I told you that usually this one is given, the input impedance, and we also have an output impedance of 75 ohms. Okay, the input impedance is 2 mega ohms, and also we have an open loop gain of 200,000. So we are asked to find the closed loop voltage gain. So how do we solve for that? So this is the solution. So we have a given. Okay, so you can see here the presentation is well presented. Okay, so the given are here. We have an input impedance of 2 mega ohms, output impedance of 75 ohms, and an open loop gain of 200,000. Okay, so first we need to find the closed loop voltage gain. Okay, so how do we do that? Or we are asked to find the closed loop voltage gain. Okay, so the first thing that we need to compute is to compute for the B. Okay, because we will be needing the formula of the B in our input impedance. Alright, So to compute for that, we need to compute for Ri over Rj, okay, or Ri divided by Ri plus Rj. Now, based from the circuit, this is our Ri, okay. So the Ri is 10 kilo ohms, and the Rf or Rj is equivalent to 220 kilo ohms. So that will be around 230, because the sum of 10 plus 220 is 230. Now, dividing 10 by 230 kilo ohms is equivalent to 0.0435. This will be unitless, no, because we are dividing it. Now, our B now is 0.0435, and then we substitute it here in the value here. Based from our problem, we have already have the open loop gain, so we just substitute this, no? And we also have the value of the input impedance, okay? So we'll just substitute the formula. So 1 plus 200,000, which is the open loop gain, and then we have the B as we have computed here, and then we have the 2 mega ohms input impedance. So what is the final answer? The final answer will be 17.4 giga ohms. Okay, now that we have the 17.4 giga ohms, okay, that will be our input impedance of the non-inverting circuit that we have. Okay, so actually we can straight away compute for what we are looking for here, no, which is the closed loop voltage gain, but we need to compute also the input impedance and the output impedance as given here. So substituting the formula, that will be 75 ohms, because that will be our output impedance, divided by the sum of 1 plus the product of the open loop voltage and the B, which is the attenuation. Okay, so the final quotient will be 8.6. This is milliohms. Okay, and the closed loop gain of this non-inverting amplifier will be equal to the sum of 1 plus Rf over Ri. So you can see here that the closed loop voltage gain is equivalent now to 23. So this is our final answer, 23. So in presenting your answers also, when you submit an assignment, so you'll have to highlight, no? So maybe you can just color your, if you are using a white background, for example, and then you're writing using a black ink, for example, your final answer, you can just put it in a different color, no? It can be red, it can be green or blue, so that it will be noticeable, no? You just change the color of the font. No need for boxes, no need for circle, because when you submit it, sometimes the box and the circle are misplaced when you submit it in Canvas, no? However, if you try to change the color of your font, so that will be okay, and that will be noticeable enough. Okay, so this is the some of the formulas for voltage follower impedances. Okay, for voltage follower, so we have discussed this already, no? The voltage follower, this is an operational amplifier circuit whose output voltage straight away follows the input voltage, and our B here, okay, the voltage gain actually is equal to 1. Okay, and our input impedance for this voltage follower has this formula. Okay, we omit here the B, but we only use this, no? And the output impedance of this voltage follower will be equal to the output impedance divided by 1 plus the open loop gain. Okay? So remember these formulas. So we have an example here of a voltage follower configuration. So we are asked to determine the input and output impedances. So we already have the formula. We just have to substitute the values from our given. So this given was also the same as this one. Okay, so we have an open loop gain of 200,000 and we have input impedance of 2 mega ohms and output impedance of 75 ohms. So we'll just want to compute for the value of the input impedance and the output impedance of this voltage follower. Okay, substituting the formula, we have 1 plus 200,000 multiplied by 2 mega ohms. That's around 400 giga ohms. That will be our input impedance. Okay, while our output impedance is equal to the output impedance divided by 1 plus the open loop gain. So that's about 75 ohms divided by 1 plus 200,000. That will be equal to 365 micro ohms. Okay, that's very little resistance or impedance. All right, so any questions so far? We have some questions. If you have some questions, you can just ask me. So if there are no questions, I can continue with the lecture. Okay, another example here. So we are asked to find the values of the input and output impedance of the below circuit, no? So also we are asked to determine the closed loop voltage gain. The operational amplifier has the following parameters. We have an open loop gain of 50,000, an input impedance of 4 mega ohms, and an output impedance of 50 ohms. Okay? So our Ri is equivalent to 1 kilo ohms and our Rf is equivalent to 100 kilo ohms. So let's try to compute for these values. So these are the solutions. Okay? So we are asked to compute for input impedance, output impedance, and the closed loop gain of the inverting amplifier. Okay, so definitely this is an inverting amplifier because the inverting input is connected to the output. Okay, so this is a voltage follower if the non-inverting input is connected to the output. Okay, or this is a non-inverting amplifier if that is the case. Okay, so now we can compute for the value of the input. The input impedance of this inverting amplifier is equivalent to Ri. Okay, so because the Ri because of the formula that was given a while ago, that in the impedance of the input impedance of the inverting amplifier is the same as its input resistor. Okay, so this is our input resistor and this is our final resistor, so that's considered to be F. We can also compute for, and that will be equivalent to 1 kilo ohms. So if you want to take to compute for the input impedance, whatever it is the initial resistor, okay, that will be our input impedance for inverting amplifiers, because uh, we have already discussed a while ago that this is similar to a voltage follower, okay, wherein the voltage gain is equal to 1. Okay, now computing for B, because we will be needing the B for our formula for our output impedance. Okay, so that will be equal to 1 kilo ohms divided by 1 kilo ohms plus 100 kilo ohms. So that's 101 kilo ohms. So 1 divided by 101 is equal to 0.001. Okay, so that will be our B, and that B will be placed here in our output impedance. Okay, so our output impedance is given, but we are computing for the output impedance of the inverting amplifier. Okay, output impedance of the inverting amplifier. So that will be equal to output impedance, which is given as 50 ohms, 1 plus open loop voltage gain of 50,000 multiplied by 0.001 plus 1. So that will be equal to 980 milliohms. Now, what will be our inverting amplifier's closed loop gain? So the formula is equal to negative, okay, RF divided by RI. So that will be equal to 100 kilo ohms divided by 1 kilo ohm, and that is equal to negative 100. So these are the answers and solutions for this particular circuit. Okay, now another term here that you will encounter is what we call the instrumentation amplifier, no? And this instrumentation amplifier is a differential voltage gain device that amplifies the difference between the voltages existing at its two input terminals. And the main purpose is to amplify small signals that may be riding on large common mode voltages. Now, some of the key characteristics of this instrumentation amplifier is that it has high input impedance. Also, it has high common mode rejection. It has low output offset and low output impedance. Okay? Now, what is this instrumentation amplifier? Actually, it is used to provide a large amount of gain for very low level signals, and often in presence of high noise levels. And the major properties of instrumentation amplifier, as I have mentioned here, are we have a high gain, okay, large common mode rejection or CMMR, and very high input impedance, now as mentioned here. Now, what is the importance of this instrumentation amplifier is that it can reduce unwanted noise. No, this is used for reducing unwanted noise picked up by the circuit. And there is also an ability of this instrumentation amplifier to reject noise or unwanted signals common to all integrated circuits pins. Okay? And is also called the common mode rejection ratio, or the CMRR. Now, the instrumentation amplifiers are very useful due to their high common mode rejection ratio. Okay? Now, we have in discussing the instrumentation amplifier, an example of that is this type of basic instrumentation amplifier, which uses, as you can see from here, it uses 3 operational amplifiers. No? So we have amplifier 1, amplifier 2, and amplifier 3. Where amplifier 1 and amplifier 2 are non-inverting amplifiers, and it provides high input impedance and voltage gain. While the amplifier tree is acting as a unity gain differential amplifier. So as you can see from here, it acts as a unity gain differential amplifier. So it unifies both the A1 and the A2. And this amplifier tree has a high precision resistor, okay, which is R6, no? And this R6 is equal to resistor 3, resistor 4, and resistor 5. Okay? So where is resistor 5 here in the illustration? Actually, this is the resistor 5. Okay? So, ito, mali pala yung drawing ko, no? Kasi drawing ko to last time. I'm using pala, in illustrating this drawing, okay, this circuit, I'm using the software called LT Spice. Okay? If you want a copy of the installer, I have an installer of this one. Okay? So, it's a very nice software that you can also use for simulations, no? So, you can for example, you can set values of resistors, values of the input voltage, and then you can simulate what is the output of this particular circuit. So we cannot use that for but I can show you some demonstrations of that maybe later, because we don't have laboratories for this, no? But this is very useful when you have a laboratory, because instead of using actual integrated circuits that may be malfunctionals, okay, or malfunctioning, so you can opt to use this simulator, no? You can also use different types of amplifiers, no? Like in this case, I'm using LT1012S8 amplifier. So basically, I'm just explaining to you the what is this how is this circuit all about, because I made a mistake here for R5, but actually R6 is equivalent. All of these resistors are equal, no, for this particular basic instrumentation amplifier. Okay, basically that is an example of a amplifier. Okay. Now, for the application of that instrumentation amplifier, it usually includes situations where a quantity is sensed by a remote device, such as temperature or pressure sensitive transducer, and the resulting small electrical signal is sent over a long line subject to electrical noise that produces common mode voltage or voltages in the line. So these are some of the example of the application for instrumentation amplifier. So we have the symbol here. So for example, we have small differential high frequency signal, and they are riding on a larger low frequency common mode signal, no? So this will somehow reduce the noise here, and this will be now the output, no, of this small differential high frequency signal. So it makes the signal better. So this is what we call now the amplified differential signal, wherein there is no common mode signal. Okay? Now, before we proceed with the operational amplifier integrator, so I think we can have a short break. Okay, let's have so maybe we can have 10 minutes break. Okay, so let's pause for the recording. Okay, so we're back. So let's discuss about the operational amplifier integrator. Okay, so this type of operational amplifier simulates the mathematical integration, okay, which is basically a summing process that determines the total area under the curve of a function. So that's basically the integral, okay, or the integration of the circuit. And the feedback element is a capacitor. So you can see from here, the feedback element, it's a capacitor that forms an RC circuit with the input resistor. Okay, so this is an illustration of a operational amplifier integrator. So we have a capacitor here connected to the input resistor. Okay, so as its name implies, the operational amplifier integrator is an op-amp circuit that performs the mathematical operation of integration. So that is, we can cause the output to respond to changes in the input voltage over time, as the operational amplifier integrator produces an output voltage which is proportional to the integral of the input voltage. Okay, the opposite of the, or the other type of mathematical simulator for operational amplifier is the differentiator, and we'll discuss that later. Okay, now the question is, how does the capacitor change? Okay, so you can see here some of the formulas, no, where Q is equal to the current in the capacitor. Okay, and this expression has a form of an equation for a straight line that begins at 0 with constant slope of IC over C. So the formula for the voltage of the capacitor is equal to IC over C multiplied by T. Okay, so that's the formula for the voltage of the capacitor. Note that the capacitor voltage in a simple RC circuit is not linear but is exponential. Now the key thing here is that the capacitor charging current is made constant. So from the illustration here, you will see that the input current is equal to the current of the capacitor. So definitely that will be equal to the input voltage divided by the current, or the input resistance. Sorry, okay? So the input current is equal to the voltage divided by its current, and the input current is equal to the current of the capacitor. So that will be the case for operational amplifier integrator. So getting back to the capacitor voltage, or VC, so this is an illustration where you can see that the positive side of this capacitor is held at 0 voltage by because of the ground, no, by the virtual ground. Now we have a virtual ground here, and the current is constant, no, and it charges the capacitor linearly and produces a linear voltage across this capacitor. Okay, and the negative side of this capacitor is the operational amplifier's output voltage. So therefore the capacitor voltage is called a negative ramp, illustrated by this example, and it is the consequence of a constant positive input. Okay, now the output voltage according to the explanation, when a constant positive input voltage in the form of a step is applied, the output ramp decreases negatively until the operational amplifier saturates at its maximum negative level. So therefore, the output voltage is the same as the voltage on the negative side of the capacitor. So whatever it is, the output voltage of the capacitor, or sorry, for the capacitor voltage, it will be the same. The output voltage will be the same as the voltage on that. Okay, so as you can see, the capacitor's negative side, which is the voltage of the capacitor, is connected to the output voltage. So therefore, the output voltage is the same as this voltage capacitor. Okay. Now, the rate of change of the output voltage is measured as the following, no? So, since the rate at which the capacitor charges is IC over C, and the IC is equal to VI, input voltage, divided by the input resistor, so taken from this formula, okay? Therefore, the rate of change or slope of the integrator's output voltage is equal to the rate of change of the output voltage divided by the rate of change of T. Now, example. This is an example of the integrator. Determine the rate of change of the output voltage in response to the input square wave. No? So we have a square wave here of alternate 25 volts positive and negative 25 volts. So this will be our input voltage. Okay. Now, the output voltage is initially 0 according to the example, and the pulse width is 200 microseconds. So the T here is our pulse, no? So that's 200 microseconds. So we can describe the output and draw the waveform after we solve it. So we have the following solution. Our formula, we will be using the formula which is the rate of change of our output voltage divided by the rate of change of the pulse. Okay, so therefore that will be equivalent to the negative input voltage divided by the input resistor multiplied by the capacitance. Okay, so we have a capacitance of 0.01 microfarad. So therefore our solution will be equal to negative 2.5 volts. Okay, this is not 25, this is 2.5. Okay, positive 2.5 and negative 2.5. So that will be equal to negative 2.5 volts divided by the product of the resistance. No? Input resistance is 10 kilo ohms multiplied by 0.01 microfarad. So therefore we have negative 25 kilovolt per second, or negative 25 millivolts per microseconds. Now our positive values, so we have to compute for that, we have the input voltage which is positive 2.5, and then we have the product also of the therefore we have 25 kilovolt per seconds, or 25 millivolt per microseconds. Okay, so that will be the solution now in determining the rate of change of the output voltage in response to the input square wave, which is 2.5 positive and 2.5 negative voltage. Now in continuation, we can also compute for the rate of change of the output voltage, which is equal to the given, so we have computed for the output voltage. Okay, so we multiplied it by the given, which is 200 microseconds. The pulse is 200 microseconds. So we will obtain now that the rate of change for the voltage output will be 5 volts. So this will be our answer. And that means that during the time the input is at 2.5 volts, the output will go from 0 volts to negative 5 volts. Okay? And during the input is at negative 2.5 volts, the output will go from negative 5 volts to 0 volts. So to illustrate that, so this will be the illustration, because here we are asked to describe the output and we are asked to draw the waveform. So this is the waveform of the rate of change. So in terms of 200 microseconds pulse. So we have this illustration, no, for the integrator, because this is the area under the curve of the integral factors. Okay. Now we also have operational differentiator, operational amplifier differentiator, and this one simulates mathematical differentiation, which is a process of determining the instantaneous rate of change of a function. Now in the ideal differentiator, the capacitor is the input element. So baligtad naman to. So when we have the integrator, we have the capacitor here, and we have the resistor here, and we have the capacitor here. But in the differentiator, we have the capacitor as our input element, and the resistor now will become our feedback element. Okay? And it produces an output that is proportional to the rate of change of the input voltage. Now, a differentiator circuit is one in which the voltage output is directly proportional to the rate of change of the input voltage with respect to time. So this means that a fast change to the input voltage signal, the greater the output voltage change in response. Okay? And the basic operational amplifier differentiator circuit produces an output signal which is the first derivative of the input signal. So we can analyze that with the formulas here, no? So we have a differentiator amplifier here. We are noticing that the capacitor is used as our input, okay, and we have a feedback element as our resistor. Okay, so the formulas can be taken as the following, no? So our current for our capacitor here is equivalent to our to the current for our input. So whatever it is, the current that is entering here will be the same as the input or the current in our capacitor. But our capacitor's current can be computed as the voltage of the current over the pulse multiplied by the capacitance. Okay, and our the current, no, the constant current is equal to the current of our capacitor. So yung current sa capacitor is equal also to the current of our resistance. Therefore, our output voltage can be computed as the current in our capacitor or in our resistor and the resistance of our feedback element, which is the resistor. Okay, and that will be equal to IC multiplied by the RF, because IR is equal to IC. Then therefore we can interchange that. Now, finally, we have the final uh, output voltage, which is equal to the negative VC over T multiplied by RF times C. So obtaining from these formulas. Okay? So the output is negative when the input is positive. So remember that. The output is negative when the input is positive going ramp, and positive, the output is positive when the input is a negative going ramp. This is a positive going ramp, therefore the output will be negative. But if the output is positive, or when the input is a negative going ramp, the output will be positive. As an example, we have an example here. So we are asked to determine the output voltage of the ideal operational amplifier differentiator, which has a triangular wave input shown. So we have a triangular input here. So basically we have a capacitor here with 0.001 microfarad and a feedback element resistor of 2.2 kilo ohms. So we are asked to get and solve for the value of our output voltage, no? So since we have a positive and negative voltages coming in our circuit, so we can get two answers here for our output voltage. So using the formula that was given in the previous slide, so we obtain the formula for output voltage as negative VC over T multiplied by the resistance of the feedback element and the capacitor, the capacitance. Okay, so that will be equal to 10 voltage. Okay, 10 volts, sorry. So we have 10 volts here divided by 5 microseconds. Okay, multiplied by the resistance, which is 2.2 kilo ohms, and the capacitance, which is 0.001 microfarad. So the answer will be negative 4.4 volts. That will be our output voltage. For positive side, so we have 10 volts divided by 5 microseconds multiplied by 2.2 kilo ohms multiplied by 0.001 microfarad, that will be 4.4 volts. So in illustration, we have the following. So here we have the illustration for the 4.4 volts and the negative 4.5 volts. So each 5 microseconds will be the phase of the circuit, no, of this particular waveform. So this will be the phase, no. So for positive 4.4, we have that one, and every after 5 microseconds the signal will have to go up and down. Okay, so from here we have the signal, and after 5 microseconds it will go up, after 5 microseconds it will go down, and then after so basically we have 10 microseconds here because this is 5, 10, 15, 20, etc., etc. So that will be equal to 5 microseconds every period of this waveform. Okay, next we have another type of the linear operational amplifier, is the current to voltage converter. Okay, so this current to voltage converter will produce a voltage proportional to the given current, and this circuit is required if you are, for example, measuring an instrument, or you have a measuring instrument capable of measuring voltages, and you need to measure the current output. Okay, so basically this current to voltage converter, it converts a variable input current. Okay, so you have a variable input current here to a proportional output voltage. So basically the output voltage will be equal to the input current multiplied to its feedback resistor. So basically ang dali lang nito, no? Compute mo lang yung ano yung current na naging input natin, multiplied mo siya sa resistance natin sa feedback element natin, which is this one. Okay? The output voltage is equal to the voltage across the feedback resistance, which is proportional to the input current. Okay? Now, in some applications, we use the voltage to current converter in photoconductivity. And photoconductive cell is used to sense changes in the light level, while as the amount of light changes, the current through the photoconductive cell varies because the cell changes resistance. So the change in resistance produces a proportional change in the output voltage. So therefore, if you change the resistance, so there will be a change in the output voltage. So we have here an example of that. We have an example of a variable resistor. Okay. Now another example. Now we have here the current to voltage. The other one is voltage to current naman tayo. No? So this one, voltage to current converter, is also another type of operational amplifier. But this voltage, actually voltage and current are the basic electrical quantities. We already know that, right? And they are supposedly they can be converted into one another depending on the requirement. Now the voltage to current converter that you see here and the current to voltage converter that we have, no, on the other slide, these are two circuits that help in many conversions, and these are also types of the linear applications of the operational amplifier. The voltage to current converter that you see here, actually it will produce a voltage proportional to the given current, no, as you can see from here. And this circuit is required if your measuring instrument is capable only of measuring voltages and you need to measure the current output. So a current to voltage converter, on the other hand, or I to V, so in the other slide that we had, so it takes current as the input and produces voltage as the output. Well, in this case, we take voltage as the input and we have a current as the output. Okay, so the formula for that is the current here is equal to the current in the resistance, no? So therefore the voltage across R1, the voltage here across R1 is equal to the input voltage. So therefore, if we try to compute for the current here, okay, the current here in our output, so that will be equal to the input voltage divided by the resistance here. Okay, the resistance here. So we're computing for the current of the output, no? So we have an input voltage and we're measuring for we're taking in for our input or for our output current. So therefore the output current will be equal to the input voltage divided by the resistance, no, here. So R1. R1 is the resistor connected to the ground. Okay? Now let's go and proceed with the nonlinear applications of operational amplifiers. So we have plenty of examples of nonlinear applications. So the first one is the comparator. So basically a comparator is a specialized operational amplifier circuit that compares two input voltages and produces an output that is always at either one of two states, indicating the greater or less than relationship between the inputs. Okay? So basically it compares the two inputs, okay, that are applied to it, to this amplifier. Okay? And of course it should produce an output. So the output value of the comparator indicates which of the input is greater or lesser. So if we have two inputs, the comparator will determine which is greater or lesser. So we have to take note that the comparator falls under the non-linear applications of the integrated circuits. Okay? For example, a comparator circuit can compare two voltages and outputs, no? Either a 1, the voltage at the plus side, okay, or a 0, for example. Okay, it's just an example. Actually, comparators are often used to check whether an input has reached some predetermined value. That's why it's comparing. Okay. Now, one application of an operational amplifier used as a comparator is what we call the zero level detector, no? And it is used to determine when an input voltage exceeds a certain level, no? So ito nga yung sinabi ko kanina, no? A comparator circuit is used to check whether an input whether an input has reached some predetermined value. Like in this case, in the zero level detector, it determines whether an input voltage exceeds a certain level. Now, for example, in this case, you can see here an input signal voltage is applied to the non-inverting input. No, we have a load here. The box here, which is green, indicates the input signal voltage applied to the non-inverting input. Okay, this is the non-inverting input. Now, because of the high open loop voltage gain, a very small difference voltage between the two input drives the amplifier into saturation. So you can see here the saturation. Okay, so when the sine wave is positive, so we have a positive sine wave here, the output is at its maximum positive level. But when the sine wave crosses 0, okay, this one, the amplifier is driven to its opposite state and the output goes to its maximum negative level. Alright, so you can see here, from the positive sine wave, we have the maximum positive level of the voltage. But on the negative, when the sine wave crosses 0, it becomes negative sine wave. Okay, you can notice that we have the maximum negative level of the input voltage. Okay, so basically we have a zero level detector using that particular example. Now, in a non-zero level, in some names it's called non-zero crossing detector. Actually, this is a modified version of a zero level detector, and it is used to detect positive signal. Instead of grounding the inverted terminal, it is connected to a reference voltage. Okay, So here are some examples of a non-zero level detector. This is battery reference. So you can see here, and this is a voltage divider reference. And this one is a Zener diode. This one is the Zener diode. Sets reference voltage. Okay? So basically, the non-zero level detector is used to detect positive and negative voltages by connecting a fixed reference voltage source to the inverting input. So you can see here the inverting input is connected by different references. Like in this example, we have a battery reference. This one is a voltage divider reference, and this one is a Zener diode reference. Now, as long as the input voltage is less than the reference voltage, okay, we have a reference voltage here, okay, the output remains at the maximum negative level. So therefore, if the input voltage is greater than the reference voltage, the output will be at its minimum minimum level. Okay, the formula to compute for the reference voltage is equal to R2 divided by R1 plus R2. Okay, so in this case, in a voltage divider reference, the formula for the voltage reference is equal to R2 divided by R1 plus R2 multiplied by the positive voltage. Okay, positive voltage input. For the Zener diode, our voltage reference will be equal to the voltage of the Zener diode. Okay, whatever it is. As an example, we have an example here. We have the input below is applied to the comparator, also below, no? Draw the output showing its proper relationship to the input signal. Assume the maximum output levels of the comparator are positive and negative 14 volts. Okay? So we have the following drawing, illustration. We have an R2 of 8. This is a voltage divider, no? Voltage divider as our reference. So we will use the formula for this one to get the voltage of the reference. Okay, so for the solution, we have R2 divided by R1 plus R2 multiplied by the positive voltage. Okay, so the computation will be 1 kilo ohms divided by the sum of 8.2 plus 1 kilo ohms multiplied by positive 15 volts. So that's basically 1.63. So therefore, in the illustration here, you can see that this 1.63 is the measure of the voltage on actually this is the point from the positive sine wave. Okay, this will be our the height of the positive sine wave, 1.63 volts. So therefore, at each positive 14 volts and negative 14 volts, we have this idea here that the voltage here for this particular pulse will be 1.63 volts. Now this is also an idea on the effect of noise on comparator operation, no? So we have a sine wave with superimposed noise here as our input. If we try to use this using a comparator, so input natin siya dito. Now it will be used as a zero level detector. So what happens to our sine wave with this superimposed noise? The input sine wave we have here will be added with the noise. Okay, so we have an input sine wave plus the noise, and then we have the resulting output here, no? We have the resulting output, which is this output. Okay, so this will be the case when we try to put this sine wave with superimposed noise in our comparator. Now, if we try to reduce the noise effects, with hysteresis. Oh, by the way, what is hysteresis? This is a technique incorporating positive feedback to make comparator less sensitive to noise. So this is the circuit that is used. This is what we call a comparator with positive feedback for hysteresis or hysteresis. Okay. Now the upper trigger point here in this illustration, we have the following formula. No? The upper trigger point voltage is equal to R2 divided by R1 plus R2 multiplied by the output voltage, okay, the maximum output voltage, positive, while the lower trigger point is computed as the lower trigger point output R2 divided by R1 plus R2 multiplied by the negative voltage, output voltage of the maximum negative output voltage. So basically, when we use it using this noise effects with hysteresis, okay, basically it triggers only once the UTP or LTP is reached. So we have here the upper bound, okay, the upper trigger point and the lower trigger point. So this hysteresis triggers when UTP or LTP is reached. Like in this example, this one is triggered, and in this case LTP is triggered. Okay. Now we also have a Schmitt trigger. This is a comparator circuit with hysteresis implemented by applying positive feedback to the non-inverting input of a comparator or differential amplifier. And it is an active circuit which converts an analog input signal to a digital output signal. Okay? Now, the Schmitt trigger devices are typically used in signal conditioning applications, especially when we want to remove noise from signals in digital circuits, particularly mechanical contact bounds in some switches. So the formula to get the value of the voltage of the hysteresis is equal to the voltage of the upper trigger point, okay, upper trigger point minus the lower trigger point voltage. So this is the formula to get that. Example. Perhaps in this example we can determine the upper and lower trigger points for the comparator circuit, which is illustrated here. Now let's assume that the maximum output voltage is positive 5 volts, and let's assume that we have a negative maximum output voltage of negative 5 volts. So we can compute for that. The formula to get the UTP voltage is R2 divided by R1 plus R2 multiplied by the output voltage, which is 0.5 times 5 volts. That will be equal to positive 2.5. Now this one is wrong, sorry for this typo. Okay, this should be LTP. The LTP is the negative voltage, so therefore the answer should be negative. So that will be equal to negative 2.5 voltage. So basically the formulas that you can use are all given, and it's a matter of analyzing the problem and substituting the given to the formula and look for what is should be determined on the problem. Okay, So I think that's the end of our lecture for this module. So if you have some questions regarding our module, feel free to ask your questions using our inbox, or you can use your microphone also.